Hello, y'all. Welcome to lesson 125 of my DB chemistry curriculum. Today we're covering reactivity 3.4.1 and 2. In 3.4.1, we're going to discuss a nucleophile as a reactant that forms a bond to its reaction partner, the electrophile, by donating both bonding electrons. We'll explain what that means. We should be able to recognize nucleophiles in chemical reactions, and we'll include both neutral and negatively charged nucleophiles or nucleophilic species. In 3.4.2, we're going to look at nucleophilic substitution reaction, where the nucleophile donates an electron pair to form a new bond as another bond breaks, producing a leaving group. So we're going to be looking at the reaction mechanisms of a nucleophilic substitution reaction. So we'll deduce equations with descriptions and explanations of the movement of electron pairs in a nucleophilic substitution reaction. So that's a lot of things to cover. We'll try and go through it succinctly, but let's just start out with what the idea of a covalent bond is, because we've looked at these many times before, and we know that a covalent bond forms through simply just the tendency to attract electrons which become shared. Seeing this idea of attracting shared electrons should automatically get you to think about electronegativity. We will be discussing that as this has a large influence in nucleophilic substitution reactions, so we'll keep that in mind. We know that similarly, this also happens in coordination bonds, which, as a refresher, coordination bonds are when one atom donates both electrons to the covalent bonds. Remember, these are also covalent bonds, so these are just types of covalent bonds. Now, we also know that when we're looking at like Lewis diagrams, we do have some molecules or atoms, we'll say ions actually. Some molecules or ions maintain, that should be a slash. Some molecules or ions maintain lone electron pairs. So right now we're building up a lot of ideas. Let's take a look at some of those molecules that have lone electron pairs just so we can keep them in mind. We might have the hydroxide ion. On the oxygen, we have 3 different electron pairs. Maybe we'll look at a molecule like water. Again, the oxygen, once again, is the one with lone pairs, and it has 2, keeping in mind that oxygen is very electronegative. Maybe in ammonia. In ammonia, we have another very electronegative element, nitrogen, in this case having 1 electron pair, or maybe an ion like we mentioned, chloride ion. Chloride has not 1, not 2, not 3, but 4 different electron pairs. Now, when we looked at things like coordination bonds, we know that electron pairs can be used to form new covalent bonds. And we're going to kind of be referencing that as we move through this section. Specifically, that lone pairs are able, or let's say not able, available to form new bonds. So these lone pairs are there and they're actually able to start forming some bonds. So how do they do that? Well, first, let's introduce the main definition of this entire section, which is nucleophiles. So what are these? Well, nucleophiles are molecules or species that have lone pairs with lone pairs of electrons. Furthermore, they are what we call electron rich. So we refer to them as electron rich because they have that non-bonding pair of electrons. In fact, they will tend to donate non-bonding pair of electrons to electron deficient species to form a new bond. So I've used quite a bit of terms here, and I'm just going to repeat some of them. When I say lone pairs or lone pairs of electrons, I'm also referring to non-bonding pairs of electrons. Those are the same thing. If we look over here, this is a lone pair of electrons, but also we can refer to it as a lone pair or a non-bonding pair, as opposed to these bonds, which are bonding pairs of electrons. Furthermore, we're saying they are electron rich, and they will try and donate those electrons to something that is electron deficient. So we're going to start looking at what it means to be electron deficient, and we'll actually explore that further in later sections. But for now, these are nucleophiles, and these nucleophiles are very important for substitution reactions. So we're going to be looking at how they are used to substitute something else, meaning fully replace it. So let's take a look at some substitution reactions. We'll just look at one quick example here. If I have CH3CH2Br, so bromoethane, and I try and add in a hydroxide. Remember, we can see our hydroxide was one of our nucleophiles. It is an electron-rich species. We can assume that it will substitute out, and specifically it will substitute out the bromine to become ethanol, CH3CH2OH, plus a bromide ion. Something you might notice is that bromide ion is actually also a nucleophile that is being let go, but we'll discuss that further as well. More specifically, what is occurring here is the electron pair on hydroxide acts as a nucleophile. And we're going to use reaction mechanism to show this as well. It is attracted to the partially positive, or attracted to the, we'll use our terms, partially positive carbon in the carbon-bromine bond. Because we mentioned electronegativity, you can always tell that between a carbon and a halide, this is going to be positive, that's going to be negative. So it's attracted to that carbon. Those electrons are looking at that carbon as something that is electron deficient. And because of that, the Br is replaced, or what we might say, substituted. So with this known, let's go ahead and, before we move into reaction mechanisms, just identify the most common nucleophiles that you will see in your DP exam. So I'm just going to star them as common nucleophiles. Usually we're going to see water with that oxygen. We're going to see ammonia. We're going to see any of the halides. And we're going to, of course, see hydroxide, but also you're often going to see a cyanide ion. So these are the common ones that the DP exam will use as you start moving forward in your studies. So with that out of the way, let's look at the actual reaction mechanism. So if you remember, reaction mechanisms are just ways to demonstrate movements of electrons in a reaction. We will use curly arrows. Now, in propagation reactions, use the fishhook arrow, which had just one. We're not going to use that this time. We're going to use a curly double-sided arrow. That represents 2 electrons. 2 electrons. You know it's 2 electrons because it has 2 points to it. The fishhook arrow has 1 point, 1 electron, that's 2 electrons. So let's go ahead and look at the general reaction for a nucleophilic substitution using reaction mechanism. So in a nucleophilic substitution reaction, the nucleophile, and I'll go ahead and label all of these, will react with our substrate, which is an electrophile plus a leaving group or bonded to a leaving group. And those will react to form the new electrophile plus or bonded to the nucleophile plus a leaving group, ion usually. So I said I was going to label these. Let's just label them really quick. This is our nucleophile. This is our electrophile. And we'll define that later in another unit, but basically it's your electron deficient species or something that attracts electrons. Remember, electro stands for the electron, phile is like. This is our leaving group, the thing that gets substituted out. And this actual whole thing right here is referred to as the substrate. If you take biology, that may seem pretty intuitive. Okay, anyways, so using our reaction mechanism, we notice that the electrons from our nucleophile are going to be attracted to the electrophile. Your electrons are always going to go from nucleophile to electrophile. As that nucleophile moves its electrons to the electrophile starts getting a more negative charge, meaning the electrons in the bond between the leaving group and the electrophile will move on to the leaving group. And it's that simple. The electrons just move straight from the nucleophile to the electrophile, then that bond goes into the leaving group, giving it the final pair of electrons. If we use polarity, so let's repeat with polarity. It becomes obvious, and I'll just write that too. Whoops, that is not how you spell that. Obvious. So let's look at a real chemical reaction with polarity. Maybe we have CH3. We'll take the same one we actually did initially, bonded to our carbon. So bromoethane, Br, plus our hydroxide. And once I throw our polarity in here, we can see between the carbon and the bromine, that's positive and that's negative, or partially positive and partially negative. And if we look at this entire molecule as a whole, that's going to be our greatest difference in electronegativities. Therefore, this carbon right here is our most partially positive section in the whole molecule. And being the most partially positive, we will see that these electrons from the oxygen want to move towards it. They are attracted to that positive nucleus. They are nucleophiles. Therefore, that bond between bromine will break and the electrons will move towards bromine, as bromine is far more electronegative than carbon. Thus, we replace the bromine and we get our ethanol, CH3, CH2OH, plus our bromide ion. And so reaction mechanisms and polarity can really help us visualize what's going on in this chemical reaction. So just to write that out in words, the nucleophile is attracted to the partially positive carbon due to electronegativity difference in carbon-bromine bond. And that carbon, I'm saying the carbon is partially positive due to the difference in the bond, not the attraction is due to that. Now, a couple things about these types of substitution reactions. The leaving group, so in this case, the bromide ion, is considered more stable than the nucleophile. We know this because it is less reactive when it's substituted. This is very similar to reactivity scales or reactivity rankings in metals. When you see that one reacts and the other doesn't, you can see that the one that reacts is more reactive and the one that doesn't is less reactive. So in this case, because the bromine is displaced by the hydroxide is more reactive. Generally, the more reactive, reactive the nucleophile, the more easily it donates, just a lot of spelling errors today, donates electrons. And this is usually based on electronegativity. Most of the time, you can just figure it out from electronegativity. The last thing I'm going to end on is one just kind of weird example. And it's how we can do this substitution to almost form these new weirder molecules. So you'll see in just a moment CH3OH. So in this case, we have methanol. And methanol can react with CH3Cl, chloromethane. Now, we know, and actually it might be helpful to demonstrate a bond here, as we're going to be doing that reaction. We saw from earlier that hydroxide was more reactive than bromine. We can reason out that hydroxide is going to be more reactive than chlorine. So what we're actually going to see here is that this electron, and I'm going to go ahead and change the color of this whole example so that I can use red elsewhere. Okay. So this electron will attack the carbon in chloromethane, as it's partially positive due to its bond with chlorine. Therefore, the electrons will move over here onto the chlorine. We get this really weird situation where we have CH3. You'll notice that, and if you're an HL, this will become more important. If you're an SL, not so important. But we'll have CH3 bonded to an oxygen, and I'm going to just turn that around. H3C bonded to an oxygen, which is bonded to a hydrogen, which is now bonded to another CH3. This is not a stable function for oxygen having three different bonds. What will actually happen is these electrons will also move onto the oxygen, leaving a hydrogen in the ether. Now, because we are creating a chlorine leaving group, what we still see is that this will replace, and we will get H3CO, CH3, and we have our leaving group of chloride ion. However, that chloride ion will bond with this H+, creating HCl. And so we still have our leaving group. It just bonds with the hydrogen that gets kicked off our intermediate. So you do get these weird cases, but this is still a nucleophilic substitution reaction. We are just substituting this chlorine with our new methanol. So hopefully this helps, and have a great day.